Nice to see many of you this early in the day. Let me get those slides up and running. So, topic to kick off the morning, something to mull over your morning coffee, is the impact of PTP-based timing across multiple industries, viewed from a software and a monitoring perspective. It's a bit of a mouthful for a title, but hopefully as I run you through the presentation and the ideas and what's going on, it will give you a bit of clarity. Hopefully the coffee will help too. So yes, I'm with NVIDIA. I'm a senior staff architect. You will notice from the slides that are up and coming, I have a foot in the networking world and I have a foot in the media world. I spent a lot of time working in media and broadcast where PTP is actually being used, but I've also worked on PTP in other areas. So just to get everybody onto the same page, because Precision Time Protocol, IEEE 1588, is not the most common protocol that is on the block. So I'm just going to run through the ideas and the concepts of how this PTP work, just to get everybody set up. We have, assuming that there's been an election process and that a so-called master, i.e. a reference clock with a time source, is available. That master will start distributing messages over the network. And the first type of message that it actually sends out is what we call a sync message. So you see on the left-hand side of the slide, the master will send this out as unicast or multicast to all the different slaves that are listening to this. And in that process, what it actually does, it draws a timestamp when it sends the message at egress. So that's the T1M. And of course, there's going to be some delay until that message is received by the different slaves. And that timestamp will occur on ingress on the individual nodes at T2S. Obviously, depending on the type of transport, the difference, the optics, serialization, interface speeds, and so on, all this comes into play around the time that it takes for these messages to propagate. So now the slave has two timestamps, which is a start to being able to compute the data it needs. What it also needs is to send what we call a delay request. So that delay request is sent individually from each slave back to the so-called master. It can be sent again as a multicast or unicast message in this case, because it's a communication between the slave and the master. And that draws a timestamp at egress at T3 slave, and then at ingress at the master T4M. But for the slave to be able to compute using the 4 timestamps, we still need that T4M to be sent back to the slave. And that is done through the delay response, which again is either a unicast or multicast message, but ultimately consumed by the individual slaves, since it's unique to the propagation time that it takes between a given master and a given slave. So now we've got 4 timestamps. We can run a bit of maths, quite simple here, which will allow us, you can look at the equations, but will allow you to calculate the offset and the delay. So through the first one, we're able to compute the offset from the master and the delay. With that, we can now process those messages, and these messages run at different message rates depending on the definition of the individual profiles in different industries, which I'll talk about in a minute. But with that information, we can compute time. So as I mentioned, there is a lot of activity around precision time protocol across industries. And this list is not exhaustive. It's an ongoing working list. And I'm not going to run through everything, but I just want to give you an idea and a feel for what it means here. So the IEEE, in its basis of the standards of 1588, which is now in revision 2.1, which was issued earlier this year, actually defines within the spec an annex which has a default profile. A profile is a way of constraining all the values that exist within the PTP. So we're talking about message rates for the sync, delay request, delay response. If it's being sent as an end-to-end system, or if it's being used as a peer-to-peer model. Different profiles, different industries use it in different ways. There's also questions about restricting or authorizing specific transports, which can be done over Ethernet frames, i.e. pure layer 2, or IPv4 or IPv6, unicast or multicast. And the different industries have different timing budgets and requirements. So the profiles are defined within those industries. For example, for telecom, it's ITU-T. There's also profiles in the IETF. The power industry, so power substations, actually have their own power profiles defined in IEEE and also in IEC. The automotive / TSN, so time-sensitive networks, have done their own profiles. And in the media space, for the audio, there is the AES profile, and for video / broadcast, there's the SMPTE profile. Beyond that, at the bottom of the list, there's also a extremely, accurate profile, which is now part of the IEEE standard, which was developed at CERN for the LHC, the Large Hadron Collider, because they needed a level of precision that went beyond what existed in those profiles. Just to give you an idea, we're talking about accuracy that ranges from about roughly a microsecond to, in the case of the CERN research profile, with sub-nanosecond. So sub-nanosecond up to a microsecond is more or less the ranges you see in terms of performance requirements. On top of that, there are other parameters which I'm not going to go to here, but that do constrain the profiles further. So my point is, we are seeing an increase in the rate of PTP. PTP originally came out in 2002 in the mostly in the industrial Ethernet industry. And then from 2008 to 2015, many other industries developed profiles that are specific to their industries. And now in 2020, we are really seeing an uptake across that wide variety of industries. It's being used in telecom, it's being used in science, it's being used in TV, it's being used in finance, and now there are actually also legal constraints around timing and references to those times. So that's the good side of things. Now, like every new protocol, new technology, especially in a time-sensitive model, there is a ramp up for users in terms of understanding how timing or PTP works. So a lot of the work has to do with understanding the basics, which is how the protocol works, but then what does it mean in terms of performance, troubleshooting, debugging. And also, there's another thing that's important, is the 1588 standard defines the messaging basics and the parts I've talked about, but not the actual behavior of the PTP stack that sits on the endpoints or in the network switches. So things like the control loop, the behavior of the servo, high band, low band, pass filters, and all the rest are not always defined in terms of how the stack should behave. That depends on some profiles. Then, of course, there's the next question is new entrants in the industry, people developing software stacks. There are multiple open source and closed source versions that are out there in the market. There's different hardware implementations because we do draw hardware timestamps when possible from the network equipment in order to increase the level of precision versus software timestamps. And the quality of the code and capabilities and accuracy combined with the debugging capabilities really vary across the board. So the problem that we have here is that the understanding of what's going on in the behavior and being able to compare apples to apples is hindered by this diversity. Now, the other thing also is that the quality of the time transfer, especially in an end-to-end environment, is affected by every single component. So serialization delay I mentioned, but it could also be fibers in terms of having an RX and a TX path that are not the same length. It could be also from a software perspective, depending on how the stack has been implemented and if it's being interrupted by other processes. It could also have to do with, am I timestamping on one NIC that is on one NUMA, but I'm actually running a software that needs to work with that PTP stack that's running across another NUMA, and therefore I'm going to have some issues related to that. So there's a wide variety of elements that come into accounting the precision of the time transfer. And of course, like every new protocol, it's yet another attack vector, so security has to be thought through. And in the case of power substations, one might say that's a critical infrastructure. Could also say the same about a TV broadcast, especially if you're doing an early warning signal or things like that. So this is another angle that needs to be monitored and understood. And then the last but not least is people are going to be developing this. So first you're doing lab staging, then you're doing early stage deployments, and then you've got the whole operational cycle where you want to be able to run this as part of your 24/7 ops, and you want to make sure that everything is covered for. Now, there are different ways of monitoring PTP, typically in-band versus out-of-band. So you want to query the offset from the slave, and that reveals you quite a bit of information, but it only reports its own notion of time. Okay, so the representation that the stack has made of time from those timestamps and the software that's running in the stack itself. Typically, asymmetries in the time transfer remain undetected through that process. PTP assumes that it's a symmetrical path. There are some provisions in the very latest version of PTP 2.1 that contribute to identifying some asymmetries, but globally, that's not the case. And likewise, if you've got issues with your control loop, those would most likely be undetected because they're running on the slave. So you really need to be able to compare the clocks with one another, both from an absolute value and a clock rate perspective. The typical model for doing that is using a 1 pulse per second signal, and that's the, let's say, de facto way of measuring. So you compare that with the source coming from the master, and in the lab, that's great, and you can do it, or you could have a number of deployments with 1 PPS to verify the signal. But obviously, depending on the size of your deployments, it's going to be a lot of extra cabling just to have a 1 PPS signal being compared everywhere. So you need to consider alternate options, because otherwise you're going to have a massive cabling issue, and you're going to start wondering why on earth you deployed this. So there are a couple of models that exist. This is a common one that's been out for a number of years. It's like a reverse PTP mechanism, also known as Netsync. It's more or less an out-of-band model if you think about it. It allows you to take, as you can see from the picture, we have the master-slave relationship, and then you've got an extra monitoring node that sits into the network, which uses the same reference as the master. In this case, we're going to take a GPS, GNSS source as the master. And they've added an extra PTP event message with a TLV, which is sent from the monitoring node to the slave node, which needs to be enhanced to support this capability. And now you have a delay request, delay response, and sync, which is reversed, and you've got the maths on the right also, that allows you to calculate the offset that is understood by the slave versus the one that is the reference from the monitoring system. Now, it is a vendor-driven implementation by Meinberg, but it is implemented in a number of multiple stacks, them being open source or commercial. So that's one way of doing it. In the latest version of the PTP standards, the one I referred to, 2.1, also the 2019 version, there's a new annex called Annex J. And there are some capabilities for monitoring. So there's min, max, and average and standard deviation, which are just identified as a means to do so. Same with delay, master to slave, slave to master, and mean path delay. And they've built up this model of 15 minutes and 24-hour slots. So there is a way to query this information, or at least it's defined in a certain way so it could be queried. And there are also message types per counters, message type counters, both for TX and RX. And this is important because when you're troubleshooting, you want to know how many sync messages were sent, how many delay requests were received, and how many delay responses were sent out to see if there is an asymmetry in the information that's being provided. There's also another clause, 16.11, which is about slave event monitoring. So that sort of draws on what you saw on the previous slide, which is the reason why I built it in this way, which allows you to have a timing data TLV with the sync messages and or the delay responses. And as you can see from the diagram on the right, the slave will then send onwards that information to the monitoring node, sort of in the same way as you saw it on the previous slide. So we see that there's bases that have come up only in the very latest version of the 1588 standard, which are now focusing on things like monitoring. So the real question here has to do with, from a unified monitoring model, which is the point of the discussion here, is saying we've got all these industries, they have all different profiles. It's like everything, you first develop the protocol, then you test it, and Over time, we realized that we need to implement security, we need to implement monitoring, and since this is time critical and it has legal implications, other than operational ones, it has legal implications, people have started to scratch their heads and say, hey, we need to really work on the monitoring capabilities. So there are some things that exist. There are vendor-specific implementations. Different stacks have different ways of reporting the information. The real problem with that is it's highly fragmented, meaning every vendor's come up with their own idea about how to do this. Some are great, some are done in a different way. And the problem, of course, is the data representation is usually unique to that vendor or even that product or that software or that firmware release. And when you go to various interop events, or you're doing lab testing, or you're trying to compare products, or you're trying to implement this in a real world network, you usually end up with a number of complications to extract the data and have commonality between the data sets. Fortunately, there are a couple of RFCs that exist. So 8173 for PTP using SNMP MIB. Now, that's a good, let's say, baseline, but as we all know, in 2020, MIBs and the sizes of these networks and the number of fields that you could have may imply quite a bit of work to get that running. The other approach that's been taken is the 8575. So there's a Yang data model that's defined for PTP v2. And that was done a couple of years ago and has some basis in there to work upon. Now, the truth is PTP monitoring, other than data, requires a number of things in terms of consistency. You need a good data definition and representation of that data. So what are the fields? What are the default values? What are the max? What are the min? How is that data represented? Is it an enum? Is it a unit 32 or whatever? All that needs to be defined so that we can correlate that information. And more to the point, afterwards, we want to compare and validate the collected data. So the second part, of course, is the analysis. And again, since we are talking about messages where you might be sending, 8, 16, 32 messages per second per node, that can create quite a lot of traffic, even though those messages are small. So the problem is not the load. The problem is if you're computing information on a precise node and you want to extract for every single one of those T1 to T4 values the information that is relevant, you can end up building large data sets across a large number of nodes, and you need to understand how you're going to get that information out of the node without hammering the CPU, for example. So you want to also come up with a model that can be transport agnostic, and it can either be pulled or pushed or streamed or whatever the model is based on what you're trying to define. So there is work that's going on, and from what we can tell, there is a trend towards a Yang data model definition. First with the work that was done in the ITF and the RFC I mentioned before, but also because of the fact that both the IEEE 802 and the ITU-T SG15 held a joint workshop at the beginning of 2020, including a session on Yang data modeling. There were other topics at that joint workshop, but one of them was around the Yang data modeling. And the point is that there is a real trend in both the IEEE and in ITU-T to try and drive forward a combined effort in this space. And in September of this year, the PAR for the work group to define the MIB and the Yang data model as part of the IEEE standard has gone ahead and started. And the idea is to take the work that's been done already in the IETF RFC and have that feed that initial process. And in the media and broadcast space, SEMT, which stands for the Society of Motion Pictures and Television Engineers, which is one of the industries in which I'm active from a PTP perspective and beyond, has been focusing on building a model to monitor end-to-end PTP capabilities and related information. So not just the information from the node, but what comes around the node that is relevant. So how does the grandmaster behave, and so on. And also, due to the fact that there are industry-specific TLVs, how is that data represented, since that data is used in order to go and generate signals for television, for example. So to take the example of the media and broadcast industry, there is a data model that's under definition, which is building on top of what exists in the MIB model and the Yang model. Why reinvent the wheel when people have done work before which can be leveraged? There's also a need for GNSS information, so it being GPS, GLONASS, Galileo, Baidu, or any other system out there. You want to collect enough information to know from your reference clock, which in most cases is going to be GPS derived. And in that case, there is a open source project called GPSD, which is used by numerous implementations, which has defined a number of fields here, which in terms of design can be leveraged. And then I mentioned, of course, there's additional data sources that are TLV specific to the given industry. I won't go into the details, but it allows you to understand, for example, the frame rate at which your TV system is running and so on and so forth. So combining all this data together over the course of the last year and a half already, is come up with a Yang data model, which is known as RP Recommended Practice 2059-15. Now, as I mentioned before, the goal is to come up with a consistent and repeatable monitoring model. And this is just an example of something that exists out there and that is ongoing. And it has taken the Yang data model approach just like IEEE and ITU-T, and it builds on existing components and it augments them where it makes sense. Right now, it's work in progress. It's what we call a stable committee draft. And the next step is what we call a public committee draft, which will be hosted on GitHub and will allow everybody and anybody to go and review and provide feedback. And the idea is to liaise beyond the technology committees that normally work with this in the model that SMT has, with the standard development organizations that are working on the same topics, software stack implementers, developers, network vendors, NIC vendors, application vendors, and so on and so forth, to be able to get as much feedback as possible to enrich the model and also to provide it to the industry as something that can be used. Now, from my perspective and the work that's going on across the industry is there is definitely a need for common PTP monitoring capabilities. There's absolutely no question about that. There are so many issues around PTP that you really get into the details when you're looking at, from a nanosecond perspective, why are things behaving, why are things degrading, what has happened, and so on and so forth. And I really believe it's critical to the success of the deployments, the validation, verification, i.e. the life cycle of using timing as a service. There is work ongoing in multiple industries, as I pointed out, it being the telecom industry, the IEEE, media, or other areas of automotive, finance, and so on. And the idea would be to try and come up with a model where we can converge those efforts to avoid overlapping or duplicating solutions, so that we don't end up all writing software 4 times for this. It does impact the timing community / networking community at large. And I think that from an OCP perspective, in my opinion, from a hardware management perspective, and also from the time appliance project perspective, this is something that could be of interest to those communities, and of course the PTP stack implementers, because you want to come up with something that works across all the different industries and across the different profiles. So for reference, I've put in the links to the different models I was talking about, so that you can go and do the specific research around this. But the point here is there is a need to come up with something, and 2020 is a great year to work on this, and there is more and more deployments. So that's it for me. Thank you. Questions?
Thanks, Thomas, for going over that. Hold on a second, please. Just click join now to come into the Zoom to talk. So we're just going to wait a little bit to see.
Sure.
The FN Tech or the streaming is a little bit delayed, so I'm watching that. They just heard you say thank you. So.
Fair enough.
So in terms of the conversation, I was wondering if you could talk a little bit more, so thanks for going over the different types of monitoring that are needed. Could you cover whether specific monitoring is, I'm trying to think, for certain use cases, like if it's within data center or, sort of high bandwidth storage applications, or if it's different for more of the broadcast. Like you mentioned, you were working on some broadcast media use cases or edge use cases. Do you see different monitoring that's needed, or is it very different per use case?
So from where I stand and trying to abstract it, I don't see much difference. In terms of the protocol works in the same way. The only thing that changes is the message rates. Okay, some are more aggressive than others because they want to attempt to use it to become more accurate. So ultimately, that's the common basis. What changes is the size of the networks and the bandwidth that's available. If you're in a sort of like IoT-like model with some edge use cases and you had very limited bandwidth, you would not want to be polling things maybe as aggressively as if you were trying to calibrate the Large Hadron Collider at CERN over 400 gig links. So there the requirements are not the same. To give you an example, in the financial markets, they need this for timestamping high frequency trading, but they also have compliances as to when operations occurred, not only in the HFT market. Then again, if you're on an enterprise/data center type of environment, you usually can spare a couple of bytes for this because the amount of traffic isn't that big. That what's going to come is going to be the more nodes you have and the deeper you want to debug, the more data you're going to be extracting, especially with these high message rates. So for me, the problem is twofold. The problem is having commonality in the data, meaning something which is representative across industries and can be used as a baseline. And the other thing is that every single industry has their specifics, so you might want to constrain or restrain part of it. Just to talk about the model that's defined in the media space, we have about 110 fields for the data, if I recall correctly, but none of them are mandatory. And the reason is, if I'm using a microphone, which is PTP synchronized, and the amount of CPU power I've got in there, I can't expect it to perform like a full-blown multi-core server. So you've got to leverage that.
Okay. Let me see if we have time for any other questions. I don't see anyone yet. Maybe just a quick question, because we only have like a minute left. Sure. What about the methods, the monitoring methods, right? I think I saw just briefly, like an SNMP MIB, which maybe, imply a certain polling rate or a certain aggregation. But if I'm trying to do, high frequency trading, debugging, it seems like maybe an SNMP MIB might not be the right.
No, so in
thing,
my opinion,
even if the data is all the same.
Yeah, in my opinion, the SNMP MIB is there for historical reasons because people wanted something, de facto default back to something that they know. But for me, the trend is definitely on using a Yang data model. That is really what I'm seeing across all the different industries, and especially because telecom has done a lot of work in modelizing data models using Yang. So they've really driven it into that direction too.
Makes sense.
And it's also them that worked on the design for the IETF RFC that defines the PTP-v2 Yang data model.
Great.
Okay.
Well, thank you very much. I really appreciate it.
My pleasure.